Section 1.5, Functions and Logarithms. This is part A of the 1.5 video, and don't be confused by the numbering. We skipped section 1.4 because that's a topic for the BC Calc exam, so this is the video that comes directly after exponential functions. To start, one-to-one functions. As you know, a function is a rule that assigns a single value in its range to each point in its domain. In other words, each input is assigned to one point in the output. Some functions assign the same output to more than one input. For example, f of x equals x squared assigns the output 4 to both 2 and negative 2. In other words, both 2 and negative 2 are assigned to 4. Other functions never output a given value more than once. For example, the cubes of different numbers are always different. If each output value of a function is associated with exactly one input value, the function is one-to-one. Here's the formal definition. A function f of x is one-to-one on a particular domain D if f of a does not equal f of b whenever a does not equal b. Let's take this apart. As we go through the course, you'll get better and better at doing this, but every time you see a definition in this really formal language, you should make sure you know what it means practically. So we're talking about some function f of x, and we're saying that a and b are two different numbers in its domain. So let's pretend that the domain is all positive numbers, which means that the numbers x equals 1 or x equals 2 are both numbers in the domain. They're saying the function that we're talking about, f of x, is called one-to-one if when I plug these two numbers in, 1 and 2, the outputs I get are different numbers. So if f of 1 equals 6 and f of 2 equals negative 3, then the function is one-to-one. But if f of 1 equals 5 and f of 2 equals 5 as well, then the outputs equal each other. In other words, f of 1 equals f of 2, but 1 is not equal to 2. So in this case, this would not be one-to-one. And that's because the outputs of two different numbers gave the same number. This is not the same thing as the definition of a function. The definition of a function is talking about the opposite statement. Make sure that you're clear on that. This is a special added thing. And when we look at it graphically, you'll realize how they're related. The graph of a one-to-one function, y equals f of x, can intersect any horizontal line at most once. This is a horizontal line test. If it intersects this line more than once, then that means it has the same y value more than once, which means it's not one-to-one. Look at the two examples. This example crosses a horizontal line only once, and that means that each of these x values have different y values. For this graph, we see 2 points that are on the same horizontal line. The 2 points are x values negative 1 and positive 1, and they both have a y value of 1. So in this case, a and b are negative 1 and 1. F of a does equal f of b, which makes this not a one-to-one function. Similarly, we can use the horizontal line test to test these two. In fact, I'll let you do that. Hopefully that was pretty easy. You're welcome to use your grapher for these. And the graphing pictures that you got were probably pretty similar to these ones on the left. The absolute value function is not one-to-one. It fails the horizontal line test. And the graph of the square root of x is one-to-one. One note on this, because I see a number of people struggling. If you're trying to put square root of x in your graphing calculator, you could use the SQRT function if you know where that is, but mostly you'll need to know that the square root of x is the same thing as x to the 1/2. So you would go into your graphing calculator and say y1 equals x raised to the, and use parentheses, 1 over 2. And that's how you can achieve this graph right here if you didn't already know that. Similarly, a cube root would be the 1/3 power, a fourth root, 1/4 power, etc., etc. Moving on. Inverses. Since each output of a one-to-one function comes from just one input, a one-to-one function can be reversed to send the outputs back to the inputs that they came from. The function defined by reversing a one-to-one function called f is called the inverse of f. The functions in these two tables are inverses of each other because the input of this leads to an output, and that output is an input in the next function, which sends the input back to the input of the original function. The symbol for the inverse of f is f to the -1 power. It's read f inverse. We don't say to the power. In fact, it's not really an exponent. F to the -1 of x is actually read f inverse of x, and it doesn't mean 1 over f of x, which is normally what a negative exponent does. In this case, that's a notation. F inverse is just the name of a new function. As these two tables suggest, composing a function with its inverse in either order sends each output back to the input from which it came. In other words, the result of composing a function and its inverse in either order is the identity function, the function that assigns each number to itself. This gives you a way to test whether two functions are inverses. If you compute f of g and g of f, remember that those mean composition of functions, then you should find that either direction, f of g or g of f, when you compute them, you get just x back. If you do, then f and g are inverses of one another. Otherwise, they're not. For example, the functions f of x equals x cubed and g of x equals x to the 1/3 power are inverses, because if I compose them, and this first composition is g of f of x, it equals x. And the second composition is f of g of x, also equals x. Let's do a real quick check, because this is a very important definition, and it's probably simpler than you may at first realize. Are these two functions inverses? I'll let you pause for a second and work it out. When you hit go again, I'll show you the work and the answer. And the answer is no. What I did to check was I simply plugged in, and I chose to do f of g of x. You could have done the opposite. But when I plugged g of x into the function for f of x, I got x plus 15 as my answer. What I was supposed to get was just an x by itself. So maybe if we had changed the f function to be minus 18 instead of minus 3, then they would have canceled each other out. But as it stands, these are not inverses. Let's check something else. If the identity function is what you're supposed to get, and we know that the identity function is just f of g of x will equal x, think about what that would look like graphically. Here's the question you're going to answer, and you'll do this one in Edpuzzle. If the identity function is the function that assigns every number to itself, that is, every input is the same as its own output, then what does the graph look like? So, knowing what the identity graph should look like, we can do this little exploration. For each of these graphs, your job is to graph f and g together, and you want to do this in a square window. Pick one where you can see each graph pretty clearly. And then you're going to graph the compositions. I'll show you how to do that if you haven't seen this before. When you go into your graphing calculator, you're going to want to find your graphing window, y equals 1. And we're going to go ahead and do the first one together here. So I'm going to type in x cubed as my first graph. And at the same time, x to the 1/3 power. I use parentheses for that fraction. And when I graph them, it looks like this. Now, my window is already zoomed in. I'm looking at the window -5 to +5, and that's both for my domain and range. So if you need to adjust it, this is what yours should look like. I've got two graphs on here. Once they're both there, it can be a little confusing to figure out what they look like. Is it a curve like this, or does it wiggle? So the trace button can be helpful to you. If you hit trace, it'll tell you that my little dot is blinking on the y1 function right now. So this curve right here that I'm tracing is y1. And by tracing it, I can start to see its shape a little bit. Similarly, if you want to switch to a different function, use the up arrow, and that'll switch over to y2, and now you can trace along y2 if you need to. So now that we have a sense for what those graphs look like, the next step was to graph the composition. If you go back to y equals, I'm going to turn off these two graphs by going to the equal sign and then pressing enter. And when I do that and move away from it, you'll see that it's no longer highlighted. So now my graph is only going to show me y2. And I made y1 disappear without erasing it, so I can quickly put it back in later. This is just y2. So I'm going to go back and I'm actually going to erase y2 as well. And what I'm going to graph in y3 is the composition of these two. If I wanted to compose these two functions, I would want to plug this equation into that one, or vice versa. There's a quick way to do that in your calculator using the vars button, and vars is right underneath your three arrows. What I'm going to do right now is, instead of using an x to the third power, I'm going to use y2 as my variable. So if I go to vars, and then I go over to yvars, hit enter when it says function, and find y2. If I now hit enter, it gives me a y2. And I'm going to use y2 as the variable, and I'm still going to raise it to the third power. This is the function f of g of x. I plugged g of x, which is y2, I plugged it into the function y1. And when I hit graph, this is what it looks like. I could repeat that process. If I go back to y equals, I'm going to get rid of the graph that we just put up without deleting it. I'm just going to make sure it doesn't show up anymore. And in the last spot, I'm going to do the opposite, where I want to take y1 and plug it into y2. So instead of that x, I'm going to put y1. I do that by going to variables, yvars function, and this time I'm using y1. And I'm going to raise it to the 1/3 power. This is the composition in the other direction. Now, remember, I'm only looking at this last composition, and we notice something pretty interesting. Repeat this process for 2, 3, and 4, and see if you can get a hint of how this all works. The next section of the textbook talks about finding inverses graphically. I'm going to go into this in more detail in class, but there's one last thing that I want you to see, practically speaking. So I will just briefly reference the diagrams, which are actually really useful, and give you the big picture, knowing that we'll go into more detail in class. Suppose you have a function that looks like this. You probably gathered this from the examples that you did a minute ago. But basically, the inverse function has the same shape, but it's reflected. And it's reflected over the y equals x line, which is a different kind of symmetry than we're used to, but one that you probably visually can recognize real easily. The reason this works has to do with the x values and the y values essentially being interchanged. If you imagine picking this graph up and twisting it this way so that that axis comes down here, you would end up with a picture of the inverse function. This gives us a really simple way to find the inverse, following these two simple steps. First, when you have an equation and want to find the inverse, you're going to solve the equation for x. Get x by itself. Then switch the variables, switch x and y. And when you do that, you'll have the formula for the inverse function. Try it for the one down here. See if you can follow those steps. Hopefully you saw this in pre-cal. And then when you press play again, I'll show you what my work looks like. Here's what the work would have looked like and my final answer. f inverse of x equals negative 1/2 x plus 2.